Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tare, and today I'm going to continue with my series on group theory. I'm going to talk about how group theory is used in physics. It turns out that group theory is used all over the place in physics. It's very important in physics, and kind of makes sense that it is because group theory comes up whenever you have symmetry, and there's a lot of symmetries in nature. There's a lot of symmetries in the universe, and for every symmetry we have, there's a group associated with it. You can apply group theory. And anyway, enough of that for now. Let's begin the lesson. So I'm going to start again by defining a group because you can't really talk about group theory without knowing first what a group is. So I did this in the last three videos I made. A group is just a set, which we call capital G here, together with a binary operator, which we call circle, or a big dot. I guess we can call it dot. So we have G comma dot, and G is just a set, and dot is a binary operation, and it has to satisfy these three axioms. Associativity, that just means that A dot B, if you do this first, dot C is the same as A dot, and then if you did B dot C first, you dot it with that. That's just what associativity means. I'm sure you guys are all familiar with that because ordinary addition, and multiplication are also associative. And then it turns out that every group has to have an element which we call the identity. That's usually written as E. We just have an element E such that A dot E equals E dot A equals A for every element A of the group. And then finally, inverse every element A has to have a unique element called A inverse, which we write as A with a superscript of -1, such that A dot A inverse is A inverse dot A is equal to E. And sometimes people also include closure as an axiom, but you don't really have to, as long as you're defining your binary operation to be closed. So anyway, that's a group. And I kind of think the starting point with group theory in physics, this is an amazing result. This is called Noether's theorem. It was discovered by a very famous mathematician and physicist, German mathematician and physicist, named Emmy Noether. She was one of the first really famous female mathematicians in the world, and she lived in Germany in the late 19th and early 20th century. And she came up with this result called Noether's theorem, which basically says, I think these are her own words, if a system has a continuous symmetry, then there are corresponding quantities whose values are conserved in time. Conserved quantities. We see these all the time in physics, like conservation of energy. I'm sure you guys have heard of that. It's kind of the basis for thermodynamics and a lot of other areas of physics, Newtonian mechanics. Energy can be created or destroyed. You might wonder why that's true. Well, it turns out it's a consequence of Noether's theorem. Because if the universe was symmetric in time, meaning that the laws of physics say the same from one moment to the next, the laws of physics today are the same as they were in 1900, same as they were when the dinosaurs were living. If we assume that, which is a completely reasonable assumption, that means that energy has to be conserved. It's just a consequence of our theory. And there's actually three kind of classical types of quantities that are conserved in physics, not just energy. That's the one on the bottom. Energy conservation is a result of time translation. The other two are spatial translation. If you assume that the universe looks the same from one place to another, the laws of physics are the same from one place to another, that fact is responsible for conservation of momentum. And since there's three spatial dimensions, there's actually three laws of conservation of momentum, or if you like, it's a vector law. Momentum is a vector with three components. So it's really three laws in one. And then similarly for rotation, since the universe looks the same if we rotate it any angle, and there's three Euler angles, there's three ways, independent ways you can rotate things in three dimensions. That gives rise to conservation of angular momentum. And angular momentum is another vector, so it has three components. So this is another three conservation laws. It actually turns out there's another three in addition to these seven, but that's the essence of Noether's theorem. Very, very powerful result. in physics. And yeah, I guess so it's spatial translation. These are just the three dimensions of space and how you can locate points in space. And like I said, the universe looks the same if you move from one location to another. And similarly for angles, these are the three Euler angles on a sphere. So you can rotate a sphere about any three of these Euler angles. And the fact that it looks the same when you rotate it is responsible for conservation of angular momentum. And there's something called the Galilean transformation. There's actually three other symmetries I didn't talk about. And this is what's known as Galilean relativity. Kind of weird because we always associate relativity with Einstein, but there's an even more basic type of relativity that Galileo discovered back in the 17th century. What he discovered was that the laws of physics are the same as long if you're moving as they are if you're standing still, as long as you're moving at constant speed, as velocity, as long as you're not accelerating. So you can do what's called a Galilean boost. You can transform your coordinates, assuming that you're moving at velocity v. And here we're assuming that we're moving at velocity v in the x direction, or to the right in this picture. And the laws of physics are the same. You can't tell. I mean, in the absence of friction, this doesn't seem obvious to most people, but in the absence of friction or wind resistance, if you were moving at a constant speed, there's no way you could tell that you were moving and that the outside world was you'd think you're stationary. From your point of view, you're stationary, and the world is moving in the opposite direction. And it doesn't seem that way because we live on a planet, the planet Earth, that has the goodly frame the earth, as Shakespeare said. I guess he didn't study Galilean relativity. But anyway, so if he weren't on the goodly frame the earth, if he were out in space somewhere, I think Galilean relativity would be a lot more obvious. So anyway, enough of that. But there's another type of relativity. I mean, Galilean relativity isn't really true because it's only really approximately true if you're moving slow compared to the speed of light. Once you start moving close to the speed of light, you have to apply something besides a Galilean transformation. You have to apply what's called the Lorentz transformation. Sometimes we call these Lorentz boost. So it's really the same idea. You're moving at a fixed speed, but you're moving at a speed that's close to the speed of light. And when you do that, not only space transforms, but time transforms too. So this looks like a shear in space and time. I know it's kind of weird, but this is the essence of special relativity. And the math involved in this is given by a set of equations similar to the Galilean transformations, but called the Lorentz transformation. This is just one transformation. This is a Lorentz boost in the x direction. And notice this factor gamma. Gamma is what's called the Lorentz factor. It's a number that's greater than 1. It's very close to 1 if you're moving close to the speed of light. It's given by 1 over the square root of 1 minus v squared over c squared. And it's always bigger than 1. It goes to infinity as v approaches c. And these are the equations of Lorentz transformation boost in the x direction, which is kind of like what we were looking at before. But you have to modify the equations a little bit. So anyway, that's the essence of special relativity given by the Lorentz transformation. So if you include boosts, where there's three boosts in the x, y, and z direction, whether you're doing Galilean relativity or Einstein relativity, that gives you 10. That gives you 10 symmetries. So if you like I think there's a name for this group. It's called the Lorentz group if you're working in relativity. It's called the Galilean group if you're working in Newtonian mechanics. But it's still a 10-dimensional group. There's 10 symmetries: one time symmetry, three spatial symmetries, triple translational symmetries, three rotational symmetries, and three Lorentz boost symmetries. So it's a 10-dimensional group. I learned this a long time ago when I was learning physics. Pretty fascinating. And not only is group theory important in relativity or Newtonian mechanics, where you're dealing with motions of big things, it's also important in particle physics, where you're dealing with very small things. And I love this picture here. This picture is showing these families of baryons and mesons. These are what are called hadrons, or heavy particles. The ones on the right are called baryons. They consist of three quarks. The quark came up from a line of a kind of a weird poem by James Joyce called Fenian Wakes, where he says, three quarks for Muster Mark. And I guess Gelman, he was the Murray Gelman, he was an Israeli particle physicist in the 1960s. He liked this poem. He was trying to think of a name. What he discovered was that people before him had thought that hadrons were elementary particles. Turned out to be a mess if you assume that, because it turned out to be over 100 of these things, baryons and mesons, and became what was called the particle zoo in the 1950s. Feynman was so dismayed by the particle zoo, he said I should have been a stamp collector. But I guess Gelman came to the rescue because he said that hadrons aren't fundamental particles, they consist of quarks. And if you look at that, let's start with a picture on the right. This is a decaplet. There's 10 particles in this picture. Um, and let's see, what are they? They all have fancy names. The ones on top, let's go from the top to the bottom. The particles on top are delta particles. It turns out there are four of them. And they have a different number of different types of quarks. I think these are all up and down. No, these are up, down, and strange. So the delta particles all consist of up and down quarks. If you notice, the D's are down quarks, the U's are up quarks. So the delta minus has three D quarks, three down quarks. The delta zero has two down quarks and an up quark. The delta plus has two up quarks and a down quark, and the delta plus plus has two or three up quarks. And I don't know if you know about quarks have weird charges. Quarks, the up quark has a charge of plus 2/3, and the down quark has a charge of minus 1/3. Those are in terms of the charge of the electrons. So before quarks was discovered, people thought that that was the smallest possible unit of charge. It turns out it's not. Quarks have third charges, but you can't free a quark. So you can't observe a free quark. That's another property of quarks. But they do exist in these particles. And I just went through the top row, and then there's another type of quark called a strange quark. So now you've got another quantum number in this picture called strangeness. Strangeness increases as you go down in this, or it actually decreases. Yeah, I don't know why. I learned this a long time ago, but a strange quark has a strangeness of -1. I don't know why that's the case. I think it's because particle physicists discovered strangeness before they discovered the strange quark. And if they know the strange quark was going to have strangeness of -1, I think they would have made it the negative. I mean, Ben Franklin made the same mistake by his convention of electric charge. Turned out an electron has a negative charge. It would have been more convenient if it had a positive charge, since it's the main, charge carrying particle that we were familiar with, and it's responsible for all of electricity, basically. But anyway, so we're stuck with that. But then if you look at the second row from the top, then you've got these things what are called sigma particles, and there's three of those. There's down, down, strange, strange, and up, strange. And I think this decouplet was discovered before Gelman came up with his model. Gelman, assumed that there was things called quarks, and then once he made that assumption, he noticed that a lot of this particle zoo was starting to make sense. There was structure to it, and it's exactly this structure. And then there's the sigma particle, or the C particles on the third row. Those are the ones with two strange quarks, strange down strange and strange up strange. That has strangeness of -2. Finally, the thing on the bottom is all strange. That's what's called the omega minus. That consists of three strange quarks. And this was not discovered when this model was made. And this is kind of analogous to, there were elements that weren't known when Mendeleev came up with a periodic table. There were these missing elements, and he predicted their properties based on the structure of the periodic table. In particular, he was able to predict their atomic weights approximately. I think germanium was an element that wasn't known when Mendeleev came up with his periodic table, but he predicted it, and he predicted his atomic weight, and he was right. And the same thing happened with the omega particle. We the particle physicists were using this model. I think it might have been Galilean himself. I'm not sure, but they predicted what the mass of the omega minus should be, and it turned out to be almost exactly what they predicted. So pretty amazing. And why am I mentioning all this? Because there's a lot of symmetry in this picture. Obviously, you can see it looks symmetric. And then there's another group of particles. This is an octet. And these are mesons. These are particles, or no, actually, these are more baryons. I think there is an octet of mesons. Mesons, I'll just mention those quickly. A baryon has three quarks, or an antibaryon has three antiquarks. A meson consists of a quark and an antiquark. And mesons are unstable because, as you know, matter and antimatter annihilate each other. Most mesons don't live very long because of that. But anyway, and they have this octet structure to them. I'm not going to go through this octet, but it's kind of the same idea. And the group theory involved in particle physics, and not just particle physics, but all of physics. You have these things called Lie groups, and you see this all the time when you're studying physics. And Lie groups and Lie algebras, there's something very closely related to Lie groups called Lie algebras. This is very, very complicated math. I don't even understand it that well myself, but I can tell you qualitatively what this is all about. So let's talk about Lie groups first. A Lie group, all that is, it's a continuous group. So it's an infinite group for one thing, but it's not just infinite, it's continuously infinite, not discrete like the integers, it's more like the real numbers. As a matter of fact, I think the real numbers with respect to addition is an example of a Lie group. It's a very simple Lie group. Just generated by a single translation along the x-axis. But there's much more complicated Lie groups. And so what is a Lie group? A Lie group is a continuous group that's also a manifold. That's a definition. And then I guess you have to know what a manifold is. Well, a manifold is really just space, like a sphere or like a plane or like three-dimensional space. Those are all examples of manifolds. They're kind of smooth spaces. There's a more mathematical definition of a manifold, but I don't want to get into that. They're locally Euclidean. That's what I mean by smooth. They're differentiable. They're not like a fractal. They're not like a mountain. A mountain would not be a Lie group. Would not be represented by a Lie group. But, a sphere or a smooth surface, would be. And then associated with Lie groups is things called Lie algebras. And this is just basically how the generators behave. So this is very complicated stuff, but it's important. And it turns out that every group, every continuous group that anybody studies in physics is an example of a Lie group, including the groups I talked about earlier, the Galilean group and the Lorentz group. I think those are Lie groups, maybe not simple Lie groups. There's some things called simple and semi-simple Lie groups and Lie algebras. You can build up any other Lie group or Lie algebra from the simple or semi-simple ones. I don't even know exactly how that works, but um, anyway, I'm just going to finish by just here's a table of some Lie groups and their associated Lie algebras. And so there's actually, these are infinite families. And I think there's Dinkum diagram. I don't think I put this slide in here, but each of these families associated with this thing called a Dinkum diagram, which is just a graph of points, and there's like 8 of them. So I think there's eight families of Lie, semi-simple Lie groups, and each of them has an associated Dinkum diagram. And there's 8 Dinkum diagrams associated with Lie groups. So I guess the simplest one is the general linear group. That's GL of n, and by the way, you can represent all these things with matrices. So GLN, that's just you can think of those as orthogonal n by n matrices, basically. Uh, because a matrix can represent a linear transformation. So this is really just a set of all linear transformations in n dimensions. So in 2 dimensions, it would be the set of all, I guess, translation and rotation. Yeah. I think, yeah, anyway, enough of that. But then there's a special linear group. This is ones where they have the determinant of 1. I think these do correspond to orthogonal transformations, which are more like rotations or reflections. They're things that preserve the Euclidean metric. So they're conformal. They preserve angles and they preserve sizes as well as angles. And then you got the special orthogonal group. Yeah, I mentioned orthogonal. I guess linear don't have to be orthogonal. And then you got unitary groups, is where you're dealing with complex coefficients. It's kind of interesting because it turns out that this SO3 is almost isomorphic to SU2. Kind of a weird fact. The set of all 3 by 3 orthogonal matrices, which basically describe rotations in 3 dimensions, and maybe reflections. I'm not sure if they include reflections, but rotations. You can think of the group of all 3D rotations. That's almost isomorphic to the 2-dimensional group of unitary transformations, which have complex coefficients. Kind of a weird fact, but there's actually a 2-to-1 map. There's more unitary. There's twice as many unitary transformations. Kind of weird because when you're dealing with complex numbers, you actually have to rotate 70. You have to do 2 full rotations, a 720-degree rotation to get back where you started. If you do 360, that's not enough. The spin will flip. Kind of weird. I learned this a long time ago. But then you got symplectic group. I don't even. Those are complicated. Those I've seen those in the context of Hamiltonian mechanics. Now we're getting into some complicated stuff. But all of these are important in physics. And then you got groups of isometries of mg. I don't even know what that means. And then you finally got groups of what does that say? Simplex. I don't even know what that is. So the last two, I don't even know what these are. I explain the ones I know. So this gets complicated, but it's important. I mean, all this group theory is basically what all of physics is based on. And you see most of these Lie groups in particle physics. I don't know why you don't see as many of them in relativity, when you're studying big things. There's sort of 4 big dimensions. If you include time, there's 3 big space dimensions, 1 big time dimension. But if you believe in string theory, there's actually, I think, 11 dimensions to the universe. So then you have bigger groups, more dimensions. Uh, I think you even use things that involve 24 dimensions. There was one time when I think string theorists thought that the universe had 26 dimensions. I don't think they think that anymore. But, they were working with 26 or 24 dimensional groups. There was something called E8 cross E8 that everybody was really excited about. That was back in the 80s. I don't think they're working with that anymore. But anyway, those are just some examples of where group theory appears in physics. And I hope I've convinced you that group theory is essential in studying physics. Anyway, that concludes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.